This video is going to cover 1.6 for UMA statistics, and we're going to talk about experiments. So in the previous section, we talked about observational studies, where you watch people and look at the effect of variables. An experiment is a controlled study to determine the effect of factors. So you're trying to say, hey, what happens if I do this? What happens if I do this? What does doing this thing cause? So by controlling things, you can look at that effect on your experiment. A factor is the explanatory variable. So different factors are different things that could be affecting the outcome. Treatment is any combination of the factors. So if you're looking at various things, if there are multiple things that could be affecting your outcome, you might combine them in different ways. For example, if we were talking about smoking and vaping and all of that, one group might smoke cigarettes, one group might vape, one group might do none, one group might do both, like different amounts of them. All of those things are different types of treatments. Your experimental unit is one person or one object, because sometimes you do experiments on like plants or rats, that is being studied. So it's like an individual in an observational study. So the control group gets you your baseline treatment. Now that could be no treatment at all. It could be a placebo, which we're going to talk about in a second, and it could be the standard. So if we know someone's sick, and we're testing a new chemotherapy drug if they have cancer, we're not going to give them no treatment. We're going to give them the standard, and that's going to be our control group. That's what's currently given, and then our treatments are going to be the other groups. Okay, a placebo it's an innocuous med. Innocuous med that looks, tastes, and smells like the real thing. So innocuous means it just doesn't do anything. It could be a sugar pill. It could be, like if you're juice, I don't know what it doesn't do anything. Innocuous just means it doesn't have actually any effect on you. But you want it to look, taste, and smell like the real thing. It's called the placebo effect. If I tell you I'm giving you Tylenol and you have a headache and you feel better, is it the Tylenol or do you think you feel better just because you took medicine? So by giving half of a group the placebo or the sugar pill, we can eliminate those people that feel better just because they took a pill, regardless of what it is. Blinding is non-disclosure of treatment. So I can't spell while I talk. Closure of treatment. So let's say we're doing a study for a new drug. We don't necessarily tell people what they're getting because, again, that placebo effect, we don't want people to know if they're getting the new med or the old med. It just takes some of that unsuredness out of the study. It makes sure we're only knowing the med. So a single blind is when the unit doesn't know. So the person getting the medicine doesn't know if they're getting the new treatment, the old treatment, the placebo, the double dose. They don't know that. In a double blind, the unit and the researcher don't know. Now, why might you do that? Well, let's say I'm doing a study for, like, my grandfather had Parkinson's. So I'm doing a study for a new Parkinson's med. And one of my friend's grandparents is in this treatment, and I really think this new med's going to work, so I want them to take the med. It's really easy to cross a line and switch that person's meds or do something, or you really want something to be better, so I might slip and tell you that you're getting the med instead of the fake med or vice versa. So by having a single blind, the person doesn't know which one they're getting, so any side effects they're telling us are honest side effects. In a double blind, it goes both ways. I don't assume that it's because of the med or not the med because I don't know which one they're getting. And it also takes away that bias or the ease for me to cross that line. And that's why you want your placebo to be good, because if one smells different, they might know just by that. So you want to pay attention to all of those details to keep it good. So now let's talk about designing an experiment. The first thing you're going to do is decide your claim. What's the problem? What are you looking at? What do you want to fix? Then you're going to look at your factors. What will affect my outcome? Some of those you're going to be able to control. Some of those you aren't. And you have to take those into account to make sure your results are good. Then you need to decide how many. How many rats are you going to do? How many people are you going to do? And you have to consider things like how big the group is, the funding you have, the cost of the medicine, all kinds of things to figure that out. Then your levels are the number of treatments. So the number of groups getting treatments. One level is always your control. That's your baseline, your traditional, your placebo. And then the other treatments, the various things. So if we're talking about the new meds, so the traditional med is one group, the new med is another group, double the new med is another group, double the traditional med is another group. All of those things are there. Then you're going to use randomization, like we talked about with the simple random or the stratified. You're going to pick a method, and you're going to use randomization to get your treatment groups. That way there's no one's picked for any reason other than that's randomly where you got selected. Then you want to replicate. So we've designed all this thing. Now you want to do it to multiple units. So you're not just going to do it on one or two people. You want to do it on a bunch to figure it out. Then you do your test and you generalize your results. So you look at what you got and say, here's how it looks or should look in the real population. So let's go back to 1, 2. We looked at this example here. Example 2 was the study. And look at what it says. So first is our problem. Oops, that's not the thing I meant. First is our problem or our claim. So research examined whether chronic exposure to radio frequency causes brain tumors. So that's our claim. Does chronic exposure cause brain tumors? Then we looked at factors. So we're thinking the different factors were 2 different cell phone signals. There was the frequency used by analog, the frequency used by digital. So those are different factors, the frequencies and the amounts. Then we looked at how many. So how many rats did they give it to? They decided 480 rats. Then level, number of treatments. So this one had 3 treatments. Group 1 had the analog. Group 2 had the digital. And then group 3 had no radiation. That's your control group, the no radiation. The other groups, they controlled how long, how often, and how long overall that they got their exposure. So our treatments were the 3 groups. Replicate, they did it over 2 years to 480 rats. And then generalize, there's no statistically significant increases in any tumor type. So that's how they said, even within these 3 groups, there's not much of a difference that we can say it's because of the radiation. So that's kind of where that comes from. All right, there are different types of experiments. One is a completely randomized design. So it's kind of like a simple random sample where each unit is randomly given a treatment. So maybe I put all 100 people's names in a hat and I pick them out, and the first name goes to treatment A, the second name goes to treatment B, the third name goes to treatment A, the fourth name goes to treatment B. You're just randomly selecting them into groups. That's completely randomized design. All right, let's look at another example. A farmer wishes to determine the optimal level of a new fertilizer on his soybean crop. Design an experiment. So the problem or the issue we're talking about is we want to know how much we're getting. So the yield, how many soybeans are we getting? So factors that affect plant growth. Well, obviously the fertilizer, because that's what we're talking about. But also sun and rain, those affect growth. If you don't get any water, you're not going to grow. Soil, things like that. All right, let's say we have 60 plants. So how many groups do we want to do? Well, let's think about how we can factor this. The sun and the rain can't be controlled. You can't control the sun and the rain. But if they're all in the same place, then it's going to match anyway, so that doesn't matter. And as long as we plant them all in the same soil, by doing that, our only treatment that we're going to worry about is fertilizer. So our control is no fertilizer. And then a good thing, if he's looking for optimum level, we want to use a couple different levels. So group A uses none, group B uses 2 teaspoons, and group C uses 4 teaspoons. So that gives us 3 levels. And then randomize, maybe we number the plants 1 through 60, pick them out of a hat, and then that's how they get put in there. Some kind of random assignment like we talked about before. Now to replicate this, because we have 60 plants, we want 20 in each group. So group A is going to get 20 plants, group B is going to get 20 plants, group C is going to get 20 plants, randomly assigned, and then we test. So we do it, we figure out what did each group produce. Did one group produce more than another? Did they all produce really good? What did each produce and how does that relate? So that's a designed experiment. All right, some different ways to create your experiments are a matched pair. So this is some kind of related pair being split into 2 treatments. So when you're doing a matched pair, there's only 2 levels. So the only option. And then you split the pair and randomly assign 1 in each group. Now, the related is something we think about. So maybe we look at twins because they have like identical twins. They have the same DNA. Maybe we look at a husband and wife because they have a similar home life. You can look at one person before and after. So if we're looking at like a workout routine, you can do their information before they work out and then after they work out and they pair with themselves. That's just one way to study the effects of a 2-level treatment thing. Randomized block is kind of like a stratified or a cluster. So you're going to divide the units into blocks, then randomly assign the treatments within each block. My spelling's great. Assign treatment within each block. Within each block. Okay, so let's say we're going back to that fertilizer thing we just talked about, but this time we don't want to just look at soybeans. Maybe we want to look at soybeans, and then we want to look at peas, and then we want to look at carrots. So we want to know if the fertilizer matters, what kind of thing it is. So there are blocks. Our blocks are the type of vegetable. Then within each block, we do the treatments. No fertilizer, 2 teaspoons, 4. No fertilizer, 2 teaspoons, 4. No fertilizer, 2 teaspoons, 4 teaspoons. By doing this, we can see if maybe no fertilizer has the same effect on all of them. Maybe soybeans do really good with B, but peas do really good with C, and carrots do really good with A. Maybe the type of vegetable matters. So that's why the blocks might happen instead of them all being the same. Finally, the block is just that group of units with a similar characteristic. Group of units with similar traits. So peas, carrots, and soy, each group is its own thing. Maybe I do vegetables, flowers, and fruit. You can pick the trait that you're dividing them by, but you just decide. So that's the vocab for 1.6. Let me know if you have any questions.